webinar. Today I'm with Professor David Coit, professor in the Department of Industrial Systems Engineering at Rutgers and a research affiliate at the Rutgers Infrastructure Monitoring and Evaluation Group. His current teaching and research involves system reliability modeling and optimization, data analysis and forecasting, and energy systems optimization. David also has over 120 published journal papers and over 90 peer-reviewed conference papers, and has been awarded several NSF grants, including a career grant. Professor Coit, welcome.
Yes, thank you for inviting me. It's a pleasure to be here, and welcome from very rainy central New Jersey, where I am now speaking into the camera. And as John said in the nice introduction, I'm a professor at Rutgers, working with Hani Nassif, except for I'm in industrial and systems engineering, working in modeling and other things. The project today, as the title says, is new degradation models, and that's what we refer to them. It's a corrosion model in this case, a new degradation models based on pre-cracked bridge direct rebars. Everything I've talked about today, everything I'm going to talk about today is based on testing and ideas from the RIME group at the Rutgers Civil Engineering. So I'm in industrial engineering. I kind of come over to do modeling. I teach optimization. I teach and work in stochastic processes. And I'm looking at this degradation data, or more specifically corrosion data, as a stochastic process. So the RIME is, has the facilities, has the ideas, has the testing. Very quickly talk about myself, and this is my research group in industrial and systems engineering. And today's talk features work that was done by the first two names you see, Jianhong Li, Jian Zhou. But I've been at Rutgers for 24 years now. In fact, I started at Rutgers the same year as Professor Khan Osbay did at Rutgers, where he worked before he went to NYU, maybe the same day even. And for most of the time, I work as system reliability, optimization, and modeling. And I guess today's talk relates to that. And some of the things we do now is machine learning to predict future degradation, but also reinforcement learning to learn which maintenance policies and plans are effective. We also work on systems, determine on-condition thresholds when best to maintain systems, and different types of optimization. Now, in the last 10 years, about 50% of my work has been on electrical power grid optimization. Kind of evolved out of my work in system reliability, and we're doing resiliency type projects, and also how to optimally expand the grid. And we've got lots of good publications and research in both. Now, right now, my students and I, and with colleagues and collaborators, are working in several areas in 3 projects. One is with my student Jian Zhou, is resiliency, how to combine hardening, which is improving the reliability of some infrastructure. Could be very simple things like simply elevating a subsystem, or it could be developing and designing a new parallel transmission line. How do we combine that with system restoration given extreme events like floods and hurricanes and things like that? Another project has to do with microgrid expansion. So somewhere like a university can, something like a university can decouple itself and work in island mode. But that requires a microgrid capabilities. For example, photovoltaic cells by themselves would not be sufficient, but you start using batteries, which are expensive, and other technologies. And the third area is today's talk. Today's talk is on this corrosion modeling of the rebars. Why? To predict reliability, of course, but also to correlate lab results where hopefully you can accelerate corrosion. Accelerating corrosion might be useful to understand it, but unless you can mathematically correlate and translate those results at accelerated conditions to field performance, then it's not being fully utilized. And that's what we're working on with the Rutgers RIME. Now, today's talk, and like always, I suppose like all professors, you know, I bring more material than I have time. And of course I know that, and I still do it, but we'll keep the talk to, you know, 45, 50 minutes. And I probably won't get through all the things at the end. I hope that's okay. But first we'll just introduce the problem. You know, a lot of learning for myself and my students. Then we'll talk, and this is not a highly mathematical presentation. Glad to talk offline, somebody more interested in that. But then I'll talk what I refer to as degradation models. Talk first just generally about degradation models, then more specifically as a two-stage degradation model and how we applied the two-stage degradation model to the rebar data. I'll probably be running out of time then, but briefly we'll talk about machine learning forecasting, because while our models, our stochastic models, are very good at predicting performance, and we can make predictions over a time horizon, in terms of what will be the degradation in the next period or in a short period of time, maybe not so good. So Zhenhong Li, as part of his master's thesis, and he's now a PhD student, did a lot of work in here. And then just briefly on future research. Now, rebar corrosion. I asked my students to just go through the news and get some pictures of some bridges and collect some data, some numbers, just to show that this is a real issue, that bridge reliability, I think most of us are aware of that. I told them specifically to get data. You know, we're at Rutgers, or pictures, I should say, from New Jersey, but they gave me this one in Georgia because the bridge actually fell over. So that's the issue. Now, the rebars. Here we see pictures of the reinforced concrete with rebar. And our study today is on the rebars, rebar corrosion. So the rebars can be made out of different materials, and we're studying the different behavior of the materials. But how will the rebars fail? Well, we look at this picture and we see now the rebar, of course, is encased in concrete. So it's protected. It's protected from the environment. It's protected from any type of contamination. But of course, the concrete cracks and the cracks grow. And as you can see along the bottom, eventually contamination takes place and the corrosion starts. Now, many materials behave that way. In fact, by behave that way, I mean the failure mechanism is delayed. Many, and of course, it's just good design as you try to protect those components which are known to deteriorate or degrade. But from a modeling perspective, it's an interesting proposition, because our failure mechanism doesn't start, and certainly doesn't start aggressively, until after a delay takes place. Well, that's good. That's good. But it makes for an interesting problem. So we're considering or evaluating new materials. We tested, and I say we, Professor Nassif and his group tested 4 different rebar materials to evaluate the performance. Some are more expensive than others, so it's important to know the performance versus the corrosion behavior. And so then, and we need testing and data analysis to evaluate the reliability and to relate reliability data that has been collected in a laboratory, and what does it really mean? Can we relate it to field performance? And that's still ongoing, but that was the goal of our efforts here. So here you see some photographs. You see a small crack forming, and then it gets larger, and then there can be the contamination, which initially is delayed, more aggressively takes place, and then the corrosion takes place, and the rate at which it corrodes increases. And those are the things we're studying. So what influences the rate of corrosion? Well, here's a list of some journal papers. I think these were put together. I think my students maybe assembled them, but they got them from Professor Nassif's student Hassan. And what we see, some of it would be intuitive, but these are studies that said, well, a crack size. If the crack sizes within the concrete are going to influence the rate of corrosion, and that's that makes sense. And also the chloride concentration will influence it, and some other things as well. We see some papers, most of them in the 2000s, one before that. In the table, you see different crack sizes and Class A concrete, high performance concrete, other things, size of the sample. So the conclusion from this work is that the crack size, the concrete cracking, is going to influence, and that of course makes perfect sense. Our goal, though, is to correlate mathematically the initial crack size with the degradation, and therefore to allow us to translate it mathematically to other crack sizes, such that we could collect data for a pre-cracked sample, analyze that data, and then make judgments about how the performance would be for concrete that maybe had no cracks at all. And that's the goal. That's our goal. That will make the accelerated testing more effective. Now we'll talk about the testing plans. Now these were things done, and we came over and started analyzing the data. This is at the Rutgers Civil Engineering Laboratory. So here at the RIME, you see a photograph in the lower right of the test lab. And the testing is taking place, many samples. I think it would be like a full factorial combination of different testing, 2 types of concrete, 2 different chloride levels, 4 rebar materials, actually a total of 5 different cracking patterns. So this data has been collected for almost 3 years. Hopefully will continue to be collected. I don't know Professor Nassif's plans. And then the goal is to study the reliability of the rebar materials, determine efficient ways to test them. And then one of the results, which I will show today, although we still need to collect and analyze more data, is to quantify just how much can you improve the efficiency specifically by testing in the laboratory at accelerated conditions. In other words, if you increase the chloride, you're going to see more corrosion, of course. But what does that mean at lower chloride concentration levels? Can we translate one to another? And that's our goal, and that's what we'll be talking about today. More specifically, we see here the different variables, 2 different chloride concentrations, 3%, 15%, a total of 5 different crack sizes, well, including no crack as one of the 5, but 2 different widths and 2 different depths, and all combinations of those. 4 materials: black steel, epoxy coated, stainless steel, MMFX. And the degradation is a surrogate measure It's a voltage difference. And as that increases, it's a sign that degradation is increasing, corrosion is increasing. And then a photograph, we see some new rebar material there, rebars there. And then we look to the right and we see, in fact, some corrosion taking place. Now, this idea of pre-cracking, here's how it takes place. We see on the left the samples with, in fact, the pre-cracks, but how the pre-cracks are done is to take these different materials with, again, 4 different widths, two different widths, 2 different depths, insert them when your concrete sample is formed. And then on the far right, we have the container for the chloride, and then the measurements take place. Again, this is going on in the Rutgers Civil Engineering Lab. Oops. So now we have lots of data. 33 months, we see on the top, the Class A concrete, the bottom, high performance concrete. The way this graph is, this is just a fraction of the data. The top is all the 3% chloride, so the lowest level. Along the bottom, you have the 15%, so much more aggressive, yet the high performance concrete shows much lower corrosion of the rebars. Another thing you see very clearly is the material behavior. The red triangles is the MMFX, and that always shows the best behavior or the least amount of corrosion. And along the top in black, the black steel has the most. Let's see, what else do you see here? Well, I don't want to get ahead of myself, but if you look, you can see some distinctive shapes. And now you can't see on these plots the effect of the crack size because we're only showing you each plot has one specific crack size. But if you could, you would see some interesting results. Also the chloride. Each one of these graphs is just a fixed number. But the chloride concentration has some interesting effect, and which we'll talk about much later. Not too much later. Now, looking at all this data, now I've taken the data, same data, and plotted it somewhat differently. Of the 4 graphs you see here, each graph represents a rebar material. Let's just look at these before we do any modeling. And what do we see? Well, one is it's monotonically increasing. Well, that's not a huge surprise. The corrosion isn't getting better by itself, where some failure mechanisms, in fact, do. If we're studying degradation of the human body, different organs, sometimes they do get better. Why is it important here? Well, our choice of models to characterize this data, the fact that it's monotonic, causes us to choose a certain type of model. Second, we see a high degree of randomness. Now, when you first look at these, you might disagree with me. So, well, they look fairly well behaved, but let me pick out and look at some interesting things. Look at the black steel, the 2 bottom lines, the purple and the red. It shows there's actually some periods of time where the 3% chloride is actually has more corrosion than the 15%. Well, that can't be really. And then there's another interesting one, where is it's also in the black steel, where the uncracked, the rebar in the uncracked concrete actually for a while anyways has more corrosion. So there is a high degree of randomness. And notice how many of the lines kind of go up and down in waves. That's not unusual at all. But now there's another observation. Maybe you've detected this, maybe not. The degradation takes place in 2 stages. First, there's this low level. You could look at MMFX and say almost no corrosion for a while. There's a low level corrosion taking place. And then at some point, it increases. So we have the first stage, and we're going to call them stage, corrosion initiation. Basically, cracks are forming in the concrete, allowing some contamination to take place. And until that takes place, we're not going to see corrosion propagation, but at some point it does. Now, I've worked in reliability and many discussions, often at lunch, with Professor Nassif. You know, how can we look at this? Well, I've worked for many years, and I do have many journal papers, and many of them pertain to this. Many of my papers are, I guess you'd say, theoretical, conceptual, some new results without an application necessarily in mind. But this is what we refer to as degradation models. Look at the graph on the left. The y-axis is labeled capital X. That's some random degradation measure. Along the x-axis, we have time. And then we see these dotted lines. These are what we call degradation paths. So even if each line represents some component or some item that's designed and operated identically, or to as close to identical as we can, there's still going to be differences. Then you see these three normal distributions. Now, I don't know how to do a three-dimensional graph like this, but try to imagine those three normal distributions and kind of tip them up on their side. And what you're seeing is those degradation paths follow some distribution. And I intentionally drew them such that the variance is increasing. It may not increase, but it often will. And then there's a horizontal line called failure threshold. I'm not really sure based on the MV exactly what that would be for the rebars, but we can make some estimates at this point until we get a better one. And basically, instead of characterizing a failure time distribution, you're characterizing a degradation distribution. But if you consider the tail of that distribution for the first two normals, they don't have to be normal, they just kind of look like normals. A portion of that tail distribution goes beyond the failure threshold. For the first one, it would be extremely small. You could say zero practically. And we model the reliability as the area between the failure threshold and that distribution. Now, we're not going to do any mathematics or just a little, but the difference is we can start to characterize and collect these distributions before failure takes place. In other words, in this instance, the corrosion, we can start to measure it, we can develop a model, we can extrapolate ahead. And if our model is a good one anyways, we can start making estimates of reliability, or when will this item be in an unsafe condition, long before an actual failure occurs. Many examples. Many things behave this way. A concrete degradation, but of course, and as we're talking about today, metal corrosion, but many other things, fatigue, wear, even illumination degradation, batteries degradation. Many things degrade like this, and we can model them. Just very quickly, I'm the first person who realized, I think he's the first person. If you talk to Professor Meeker, he might say, I'm sure he'd say he was motivated by others. At Iowa State, he demonstrated that we can replace much of reliability theory or supplement it with this degradation modeling and make reliability models and predictions before observing failures. Meeker's been a professor at Iowa State since '75. I was lucky enough to visit him, I forget now, about 10 years ago. And I see him from time to time. So he's been a professor, let's see, 45 years. I don't know how old he is, America, it's rude to ask, but if I ask him, you know, what are your future plans? He'll tell you what he's doing 5 years, 10 years, anyways. So he's formalized this degradation modeling, and there's been now a lot of work, and I'm going to apply some of these models to the rebar. Meeker's original model we refer to now as a random effects model. It's actually pretty simple. We fit some sort of regression line or some other relationship, maybe nonlinear regression, to the degradation data, but then the parameters in the model, at least some of them, are random variables. There's a gamma process, which between any 2 points in time, the change in degradation is a gamma distribution. There's a Wiener process, very popular, but that's not monotonic. Overall, it will show an increase in degradation, but momentarily decreases as well. And there's others as well. Based on everything we know and have learned about the rebar corrosion, the gamma process seems appropriate. It's monotonic, seems to fit the data in certain extent. Now, back to the data. What did we see again? There was 2 distinct stages: corrosion initiation, corrosion propagation. And in a general paper I have under review now, I call it failure mechanism initiation and failure mechanism propagation. And the other thing we saw, though, is crack size and chloride concentration affects it. You can see it in those graphs. So that led us to more detailed study. And we say, well, that's not just understandable, but physically correct, is that there is this process of corrosion initiation that needs to take place. And then finally, the propagation. And we've written now 2 papers. The first paper is under review now. I'm not going to talk about that for more than about a minute today, because I'll run out of time. That's another theoretical type model where I'm simply using this as motivation. And then there's a much more practical paper, which we still have not finished yet, but almost. It's similar to today's talk, that talks specifically about how a model that relates the corrosion at different crack sizes and different chloride level, how a model allows us to translate among different chloride levels and to test in an accelerated condition such that we can make judgments based on something in field performances. And we're not there yet. That's where we're heading. So we have these 2 stages, stage 1, stage 2. That long list of degradation models I showed you, including the gamma, well, they don't correctly follow or consider these 2 distinct stages. But I asked my students, I said, is this unusual? This to have a failure mechanism at 2 stages? And after doing some research, they said not unusual at all. In fact, it's very common. In fact, extremely common, because think about it. If you're going to want to design a reliable product of any type, whether it's a bridge or anything, you're going to want to have some forms of protection to delay the failure mechanism. Think of your automobile, and they put protective coatings under the bottom. So those of us who live in the Northeast, I'm from Syracuse, New York, where it snows a lot and there's salt on the roads. So we consider, well, are there models for that? Yeah, there are 2-stage degradation models. We see here the red and the green line, and this would be the expected value. So we've taken away the random variation. But what we see is that at some point, the degradation fundamentally shifts. And there's been work done. As I said, we recently wrote a paper, and there's differences. One is, what causes it to shift, and when does it shift? There's a certain type of model with an alarm threshold. That's what we're going to assume for the rebar corrosion, which means when the degradation or corrosion reaches a certain point, it then starts to increase. But then there's other examples where there's a first hitting time, meaning there's a time period, fixed or random, where the shift takes place. Now, within each of the stages, it can have very different behavior. Gamma, inverse Gaussian, Wiener, others. And so also, the students, and this was with some assistance of my friend and colleague Liran Tui, put together this list of work that had been done in two-stage degradation. And we see there's fixed versus random change points. You can have one change point or more than one. You can have defect-based failure modes or duration-based other things. Now, none of these models have covariates, which we're going to propose for the rebars. By covariate, I mean stress variables. Stress variables which will influence those stage 1 and stage 2. I need to move more quickly. So there's many of these models, but we're looking at ones that are referred to as two-stage stochastic process, and specifically a gamma. In other words, the first stage has a gamma process, second stage has a gamma process. Based on everything we've learned and data analysis, this seems to be the appropriate model. And here's a reference. Don't know if it's the first one, it's just a particularly good reference on a gamma model. Now the models we're going to propose. First, a gamma. We have two stages. A gamma process, again, means between 2 points in time, the change in degradation is a gamma distribution. A gamma distribution has two parameters, a shape parameter and a scale parameter, alpha and beta. And what we've done here, it's a little confusing because both stages are gammas. So we have alpha, I guess I don't show it here, we should have. Alpha subscript Roman numeral 1, alpha subscript Roman numeral 2, etc. But the students, and if they're listening, they did a tremendous amount of work. We want to know, where should the covariates go? In other words, does the crack size and the chloride influence the alpha parameter or the beta parameter? And we tried different possibilities, and the expected value, the expected degradation amount, is alpha T divided by beta. So you could put it either place. It won't influence the expected value, but it influences the variance. So we see on the left a gamma distribution or a one-stage gamma, and on the right we see it fundamentally shifts. Now, let's go specifically to the rebar data. We developed a model for each of the four materials. Separate models. We didn't try to combine the data for the four materials. So this is black steel, but most of them are the same. So we have the alpha parameter and the beta parameter. Now, the depth of the crack seems to be much more important than the width. We tried putting them in the model separately, and then we saw that width didn't really influence it too much. So we could leave it out, but then it's not too surprising. We said, well, let's just do area. And that seemed to work best. So we have the 5 different crack sizes, and so we have area, width times depth, not too difficult. But we see along the bottom there, the beta parameter, this is for stage 1, is a function for the crack and the chloride level. So a bigger crack, and it will, the corrosion initiation will take place sooner. Well, that's not a big surprise. That's not a big surprise. In fact, no one should be surprised at all. But what's the important thing here is we modeled it. So I can vary, look at that function. I can vary A, I can vary C, and get performance predictions for other values in A and C. Where if you just looked at the data in isolation, this crack size, this amount of corrosion, and someone asked you, well, what about smaller crack sizes? Well, without a model, you don't know. Okay, let me go more quickly. Stage two. Stage two, once the corrosion was initiated and we're just propagating, the crack size didn't seem to matter too much, but the chloride did. We could, and so we have this relationship with just chloride. Now, our model. Now we have 4 different graphs here, but this is all stainless steel. Stainless steel has sometimes more randomness than the others. And this is not curve fitting. This is our model prediction. So you'll see some that aren't quite right, but mostly they are. Mostly they are. And by having a model, we can then have the expected time that you see here until corrosion reaches a certain level. If we can define later a failure threshold, it would be the expected time till it was in an unsafe condition. But now we have a function. This is for stage 1, which is T1, stage 2. Furthermore, we can take the derivative of that and we can have degradation rate, again, as a function of the crack size and the corrosion. And so we've computed all those for all combinations. And you know, we see here, and this is in stage 1, black steel with a big crack size, and a high chloride concentration, not surprisingly, has a very high degradation rate, whereas the MMFX has low. Now you notice if you look across the MMFX, I have the same number. I want to be clear here. It isn't that the crack size has no effect. It's that the MMFX did not corrode in stage 1 at a very high rate. And any effect caused by crack size, we could not detect. We could not detect. But don't anyone take from this table that crack size doesn't influence it. Based on the natural variation in the data, you saw the data, we couldn't observe whether changes in the degradation rate were due to the crack size or not. In stage 2, we see much higher degradation rate. Not a surprise, not a surprise. Now, this is for all materials. Well, we don't have space here. This is just for 3 of the 4, but actual data versus our model. Notice the distinctive shift. The distinctive shift from stage 1 to stage 2. There's some exceptions. You can find them by looking at them. But in general, we can fit the data pretty well. We can fit the data pretty well. We can't explain all the ups and downs in the data. But overall, the model fits the data pretty well. And again, this is like if you look at the 3% and the 15%, this is one model. They come from the same equation. Now, the other great thing we can do is get acceleration factor, AF. What does AF mean in words? 1 hour in the laboratory translates to AF hours of field performance. Now, in theory, and the graph on the left is from the more conceptual theoretical paper, we happen to know that the chloride affects both stage 1 and stage 2. But in practice, and in a general model, we could have one vector of stress variables that influence stage 1 and a whole other vector, stage 2. They could be the same, they could be partially the same. But you see on the left, the first graph, we're accelerating just stage 1 and then observing stage 2. Second graph, we're accelerating just stage 2, or we accelerate both. Now the equation you see there, AF, I label it as mean time to failure, where failure would be is in an unsafe condition. At the subscript O means nominal or actual. Subscript S means high stress, stressed. So I can relate the two of them together, and just quickly, I do that by having a separate acceleration factor for each stage. And then I can mathematically combine them based on this P1 and P2, and they're actually pretty simple. And remember, I have the equations on the previous slide for these expected times. P1 and P2, simple. P1, the proportion of time spent in stage 1 P2, the proportion of time in stage 2. So we can develop these AF relationships, and we can see, we can accelerate, again, based on because, based on our model and our data, and we have more work to do, but I can accelerate stage 1 up to 60%. And really what we want to see is the stage 2. Well, but no, that's not true. We want to see the combined, but I can accelerate stage 2 up to 23%. Now, a lot of numbers here. Tables 1 and tables 2 tells me the percentage of testing time reduction by pre-cracking. In other words, by putting those artificial cracks in, I'm going to observe a corrosion earlier. Again, that's not a secret. That's of course you would, but this tells me specifically what proportion of time is being reduced. In other words, I can test it a certain amount, get some results, and I've reduced, if I tested it under normal conditions, by how much. And so we see numbers up around almost 30% a reduction. That's just for stage 1. Combine stage 1 and stage 2, and that's the table number 3. And we can see also a reduction. And that's what our model is allowing us to do. I won't go over this other than we used everything you've just seen as motivation to develop a brand new model I refer to as a Weibel gamma 2-stage model. This is a paper currently under review. Jen Zhou, Jinhong Li, Hani Nassif, and myself under review, and hopefully get published, where we did a brand new model where stage 1 is a time to event Weibel distribution. Stage 2, though, is a more traditional gamma process and very elaborate. And we notice here that stage 1 is a completely different function, but still area and C. Now, in my remaining time, I'll go 5 more minutes. Machine learning. My student, and I'm learning from them, let me be clear. Everything up to this point, I hope my students would say they're learning from me. But the machine learning forecasting, I'm learning from them. And the final piece of this is we can develop these models. We can predict reliability. We can accelerate in the testing. But I want to predict the next period of time, or the next several periods of time. Those probabilistic models that I showed you don't work very well. Well, I mean, that's not what they're for. It's not what they're for. It's not that they don't work well. It's not their intended purpose. So we did some machine learning. So first, some just traditional autoregressive models, if that's referred to as machine learning, I'm not sure. Back propagation neural network, and then a more advanced long short-term memory, radial neural recurrent neural network. And let's just show you some of the results. We have the data, and our machine learning algorithms, they're going to be based on these covariates. Here we see in the table depth, width, which we can multiply and get area, chloride level C. And here we're going to use the previous months to predict the future months, either the previous 3 months worth of data or the previous 5 months. First, just an autoregressive model. What does that mean? AR3, AR5, I'm going to use the previous 3 months plus the stress covariates to predict the next month, or the previous 5 months to predict the next month. And so what we're going to do here, I got my question, is I'm going to use months 1 through 28 to predict months 19 to 33. Now this is the autoregressive, where I don't need to do the same type of training as I do in the neural network. But here, I'll show you some results here. And this is, I guess, not a traditional autoregressive model because we have these stress covariates. But you can see that nothing really. You can look at the far right, you can see p-value. You see everything. Now for this particular data, and you see the previous 3 measurements or the previous 5 measurements. This is actual versus field for all of them. It's hard to really get much out of this plot, so let's look at it this way. This way, we're looking at the record number versus the response. Again, it's hard to see here, so let me help you out. In the first and last stage, we tend to overestimate the corrosion. In the middle, we tend to underestimate. Now, let me go on. Now, a neural network. Again, we're going to use months 1 through 28 to predict 29 to 33. But as you know, months 1 through 28, I need a test set and a training set. And so we have 85% of the data to be the training set. So we predict the neural network, completely a traditional backpropagation, multi-layer neural network. I think I forget now, but 3-layer neural network. Backpropagation going one way. And if you look at our data, sometimes we have a very good fit, and I don't necessarily explain. I can't explain why we have a good fit and sometimes not so good. But you see over here, this is for what? This is all black steel. We have also the results for each material. When we have large crack sizes, but low chloride, our model, the neural network's almost perfect. But over here, when we actually have small crack sizes, which should be easier to predict, I would think. But high chloride level, the model, not so good. Now let's look at the final months. Now keep in mind, this is a pure prediction. We do pretty good. Again, 1 through 28. Not always though, by the way, not always. 1 through 28, and then the red circles, which I've gotten big here, that's a prediction on 1 through 28 for the final ones. Now, the final model, then I'm out of time, and which is fine because this is something my graduate students are teaching me, but they're a more advanced machine learning where the memory, there's forgetting and there's other things as well. For the, let me finish these, just a few more slides and my time's up. But so we have this long short-term memory and there's some forgetting, but yet there's some long-term memory that can return. And we seemed, and I won't be able to explain this, but I know from the data reported by my students, we get some good results. Now, and it trains faster. Now my time's up.
Yeah, so let's move into the Q&A, and we can start with this question, but I'll just tell the group if you have any questions, you can feel free to.
Let me just, while they're doing QA, I'll show this one final slide, because this is the final thing we want to do. Relate to this data that's been collected field. And this now has not been done, but we want to correlate everything I just showed you today to now this data on this. And so thank you very much. That concludes my talk.
Sure, and thank you. And I'm sorry we have to cut it a little bit short.
I'm done.
We have one question from the group, but before we begin, maybe Dr. Osbe, would you like to say a few words?
Yeah, David, sorry I couldn't talk because I was muted by John. So thank you for doing this. This is a great presentation. I took a few notes and I really like it, and some ideas, not necessarily in this, but in other research that we do. So as you said, this kind of research can be used for other areas also. I mean, so that's really good. But again, thank you very much for taking time. I know you can't go out and ride your bike, so yeah. I don't feel guilty keeping you at home. So it's terrible weather. It's raining the whole day.
Yeah, raining very hard all day. Are you in Princeton now? Or?
I am in Princeton. Yeah. I mean, one question I have. So of course, it's also important to kind of remember the type of stochastic process you're modeling. No? So this is, I mean, in control theory, we call this like a slow moving system. So things do not change like on a day-to-day basis, at least I'm assuming, you know, so, so that might create some challenge, no? I mean, if you talk about transportation, for example, things change quickly, you know, in terms of, let's say, travel times, you know, but the amount of corrosion in this kind of system might take, I mean, forget about MMFX steel, but even normal steel, it might take longer than hours, you know, to change. So does that create a challenge when you do your modeling? So it's, I mean, relatively like a static system time-wise.
Yeah, and I'm going to say no, not at all. In fact, in some regards, you know, it might make, you know, it might be less of a challenge. You know, since it is slow moving, it's a case of just modeling it the best way and not making incorrect assumptions. And I guess maybe what you said is making sure we're picking the right stochastic model with the right covariates. And of course, we did the functional form of the covariates based purely on curve fitting, and then it went well. But what the challenge is, and what I want to continue to do is there physical reasons? Is there physical relationships? My guess is there probably is, that could show where and what the functional form is of those. You know, it's a little bit unusual to have the gamma process. Nah, not that unusual, but somewhat unusual to have the gamma process parameters a function of these covariates. And of course, we're treating the covariates as deterministic, and that's an assumption too. There's another type of gamma process where the parameters, the coefficients within the model can be random variables, and that's, I forget the name of it. So, you know, we have different types of things we can look at, but so far, you know, I mean, you know, we've been working on this about, oh gosh, a while, you know, over a year. And so I think our models are pretty good. Now, do I think they're perfect? No. Can we improve them? Yeah, we're going to.
So one thing I might have missed. So you said the area appeared to be the factor that affects, but the depth. So you don't have the depth. So you only use the area as the.
No, both. I mean, area is depth times width. So the depth is actually the most important.
Okay. I thought area is like how, you know, big the crack is, but you're looking at also the depth.
Yeah, we had a pretty good model with just depth.
Okay.
And then, but we said, well, width had some effect, but then for some of the materials where there wasn't that much degradation, it actually showed, you know, I think there was one material that showed that the depth made it better, you know. I mean, I'm sorry, the width made it better. I said, no, we can't, you know. So when we multiplied depth times width, we got good, consistent results. If I recall, you know, always. They made sense physically, they made sense mathematically. But we could do this with just depth. Depth is much more important than width.
That's what I was thinking. Yeah. All right. Good.
So, okay. All right, very good.
Maybe we have one more question, which is if the corrosion initiation time was a random variable, could the predictions be improved?
The correlation initiation time
corrosion initiation time.
It is a random variable. And now, so we have this random, and so the answer to that is yes, but it is already random. And in fact, the main difference between the gamma I showed you. So for the gamma, I've got this stochastic gamma process. Now our model is what we call this alarm threshold, meaning that this random gamma process, whenever it hits the alarm threshold, and let me talk very briefly how we got the alarm threshold. But first, let me say, then it triggers it, and it goes into stage 2. So it can hit that alarm threshold, you know, anytime. Oh, not anytime, but it's a random variable. Now, how did we select the alarm threshold. We did it purely based on observing the graphs. And one thing we observed that made us go to the alarm threshold case is that I might accelerate or decelerate degradation by changing crack size and changing chloride, meaning the graphs are going to be to the left or to the right. And yet, and this change, every material is different, let me be clear on that. But for each material individually, we're consistently seeing that when the degradation hits some point, it's shifting. Now, whoever asked that question, I agree entirely, because I showed just 2 slides of another paper we did. And that paper is based entirely on that observation, because I took more directly the corrosion initiation period and I modeled it as a Weibull distribution. And then so we shifted, it's the first time ever, I think, we shifted from a time to event distribution, like a Weibull, and then we transitioned to a stochastic process. So that's absolutely the way we're thinking. And so good point, but we agree.
All right, thank you so much. I think that's all we have time for. Thank you everyone for attending.
All right, let me just say my final note. You know, I can't see who's there, but you know, I know John's there, I know Khan's there, and you know, a couple others. But anyone, feel free to, if you're interested, send me email. It's you can get the email from John. I'd be glad to answer any questions or send some of my research papers, etc. Okay, thank you very much.
Professor Coit, thank you so much. And thank you everyone for attending. Please feel free to follow C2 Smart on Twitter and join our mailing list to hear about upcoming webinars. Thank you.
Thank you, David. Thank you.
Okay, see you guys.